Okay. So, we will do some conservation laws for field theory, okay, and this plays a very important role. Some is obvious, but one non obvious thing will come in today's lecture. So, this is Lady Noether, okay. She she struggled quite a bit. In earlier times they were not, women are not allowed in universities. So, she was working as assistant of Hilbert, then but this theorem is very important, and appears in all areas of physics, okay. So, we will just I will show you the how it appears, but we did it for particles in the beginning, right, I mean in the last lecture and one of the last lectures, but we will do it now for fields. Okay. So, the derivation. So, let us just look at what is the essential aspects of Noether's theorem. In fact, the derivation in fact is a simple derivation, but okay, some people are more, some derivations are more detailed, but you will get the essential idea here. So, it is a change in Lagrangian, okay. We are looking at change in Lagrangian, and of course, in when derivation of Euler Lagrange, we make a constraint that the we vary the phi, vary the field in such a way that at the end points the field should not change, right. For particles we make sure that the end points, the positions are same. For fields you have to make sure, as I said, initial condition and final condition, the field must be the same. In between you can vary the fields, you can apply perturbation and so on, but there is a field configuration. So, please remember Euler Lagrange equation tells you that there is a configuration of the field which goes from initial to final, which minimizes action, okay. So, that is a, and that is what we see in classical solution, that is a classical solution, okay. But here I am going to not constrain that phi to be the variation in phi to be 0 at both the ends. We will say that, well, you can choose whatever phi you like, I am not going to constrain it, but under that constraint what is delta L, okay. So, we look for the delta L. So, that constraint is not imposed now. So, this is a well, I mean delta L, change in the Lagrangian density, okay. Let us look at change in Lagrangian density. So, delta L delta phi plus delta L delta mu phi multiplied by delta mu. So, this is a derivative. So, the Lagrangian can change due to derivative in phi in a change in phi as well as due to change in the derivative. These are two contributions. We rewrite it, this part remains as is, the first part. The second part I am going to, so this is pi mu of x, right. This is the definition of the momentum density, okay. So, this is that, and this is I am basically commute the derivative at delta, which is allowed, okay. So, change in the derivative of delta phi, okay. So, now this term is a derivative of the second function, right, it is of that form. So, now we are going to use the product rule. So, this part is rewritten as derivative of both the f g minus derivative of the first function g, right. I mean I am basically doing nothing more complicated, g equal to del mu f g minus g del mu f. No, I mean this is the product rule. So, that is what is being done here. Now, combine these two, delta phi is outside, great. So, delta phi is arbitrary. So, this is coming here and this term is coming here. Now, Euler Lagrange equation is still valid. So, what happens to the first term is 0. So, whatever delta phi you choose, it does not matter, the first term is 0 and this is the second term. Now, typically we want delta L to be 0, okay. Delta L I want, well no sorry, I do not want delta this, sorry, I made a mistake. I want to write this as a del mu, I just rewrote that. So, we write delta phi. So, basically delta phi, okay, there could be many component of phi and so on. So, we want to parameterize phi in terms of a parameter lambda. Right now phi is only one component, but I may have more components. So, we write delta phi as some parameter delta lambda multiplied by d phi. This is a derivative phi. Okay. So, then we write, so this is the definition, okay, and then we say that this is current. Okay. In fact, I am going to set that to 0 indeed delta L. So, this is defined as current, N is for Noether, okay, J mu is a current, is del mu, pi mu. So, this is pi. So, this part I am going to write as delta lambda is outside, okay, keep delta lambda outside. So, this is a function, we call it current, Noether current, okay, and it has an interesting consequence, just hold for a minute. Okay. Now, we want delta L to be 0, we set it to 0. So, I do not want change in Lagrangian. Okay. Under this perturbation Lagrangian should not change, but my perturbation is arbitrary perturbation on phi. So, if delta L is 0, then that means this quantity must be 0. Okay. So, this divergence of the current is 0. The divergence, no, the del mu means divergence, but it could be 4 dimensional divergence. Okay. In 1D is going to be one space one time is going to be dt j0, this is j0 plus dx j1 is 0, again 1D, but in 3 dimension, 3 space dimension and 1 time dimension, j0 plus divergence, space divergence, okay, is 0. Okay. So, all the sum of these derivatives. So, that is why you need to kind of do it as an example. I will probably give you some homework. I am going to show you some real examples, but you need to do more. Okay. So, this is the content of Noether's theorem. Well, one more slide, I am going to show you what you can derive from Noether's theorem after this. So, divergence of a current is 0 and that current is a Noether's current. Okay. So, we rewrite, so let us do the space integral of that Noether's current. Well, del mu j mu is 0. So, that means their integral also will be 0, but I am doing space integral, not the space time integral, okay, this 3D space integral. So, now this divergence I write in 2 components, this is a time derivative and this is a space derivative. Okay. Now, what happens to the space derivative? What is space derivative, integral of space derivative of divergence of something? Gauss theorem will tell you 0. Of course, the current at infinity should be 0. Okay, that is what we will assume the field is basically vanishing and there is no current. So, the second term is 0 by Gauss's theorem, second term. Okay. So, what does the first term give you? So, this derivative with 0 is means d by dt. So, d by dt of j0 integral d cube x is 0. Now, d by dt can be taken out, right, or you can take the d by dt out. So, this quantity is constant and this is called Noether charge. Okay. So, there is a conserved quantity and that is the derivation. So, this charge q n is constant. Okay. So, for every conserved, every symmetry will get a conservation, okay, every symmetry operation. Okay. So, let me just make this comment. So, delta L will not be 0 for arbitrary change in phi. Under some symmetry delta L will become 0. So, if I change phi in arbitrary way, I will not get delta L to be 0. For some symmetry operation delta L will be 0, that will imply, so let me write this, symmetry of delta phi, okay, some symmetric variation of delta phi will lead to delta L to be 0, okay, and this will imply some charge conservation, some quantity will be conserved. Okay. So, we need to look for variations of phi in such a way that my Lagrangian density is unchanged, and that immediately gives me a conservation law. So, that is a line of logic. Okay, clear? So, let us do some examples. So, I will give you 4 examples. Okay. So, time translation for Schrodinger equation. We can do it for Dirac equation and we can do it for Klein-Gordon, but let us illustrate by Schrodinger equation. So, I give you the Lagrangian of Schrodinger equation. Okay, that was the motivation why we are deriving Lagrangian for Schrodinger equation. Okay, so this is my so I am going to make change in psi by translation in time. Okay, so I have this psi, but so this I xt, but I say, well, I am going to change time to t plus delta t. Okay, so psi is exponential I e t some stuff phi x. Okay, so now I make this psi. Okay, I mean I am just writing some jumbled up some stuff. So I make change. So time translation means what? The wave function right now or wave function sometime later. So I look at the wave function sometime later. Okay, that will be different function. But everybody understand what is meant by time translation? Okay, so let me just go back a little bit to motivate. So if I do an experiment in a lab, okay, let us do an experiment in the lab. These particles are coming and colliding and they are just getting scattered off. Okay, I do it today, I do the experiment tomorrow. Assume that the room has got no change, like there is no electromagnetic stuff or some. So room is same environment. I do the experiment tomorrow. I should get the same observation, right? The particle will scatter exactly like that in tomorrow as well. So that is laws of physics are invariant under time translation, and that has a very important consequence, which I am going to come here. What is the consequence of this time translation invariance? Of energy is concerned. Okay, so that is what we will derive it here. So of course, well today and tomorrow we will do a new setup, but imagine that I look at this trajectory now and 1 second later. Okay, so that is a translation. I'm translation in time. So my variables will change, right? My fields will change. So that is what we get this field change. So what is the change in psi? This is the change in psi. Now dt is t is lambda for me. Okay, so I remember I wrote this as d psi times d lambda. So this will be d psi and this is d lambda. Okay, so d psi, this d operator psi. I want some smooth function. I do not want to carry this delta and so on. So this d psi is psi dot. Okay, so that is change in the function, wave function. So this is my Lagrangian. I wrote like that. Now Lagrangian I am using the old Lagrangian. Okay, so without the d by dt of f. So the current we can write down. So ignore this. So this is something else. This is the current I wrote, right? Now another current pi mu del d psi, and pi mu we know how to compute pi mu. Pi mu is this one d partial L partial psi dot. Okay, that is pi mu. That is a definition. Now right now I had two components of the field, psi and psi star. Okay, we need to sum because otherwise I will not get a real energy. I mean the energy must be a real quantity, so I need both psi and psi star. So I am doing it for both psi and psi star, that is why I am summing over components. So momentum is partial L partial psi dot for psi, and there is a partial L partial psi star for psi star. Multiply this by this del psi d psi. So for psi this is going to be psi dot, if a psi star is going to be psi star dot. Okay, correct. So this is going to be I by 2 psi star psi dot, and other one is just complex conjugate. Okay, this component is just complex conjugate. So, that is why we get real thing. So, I psi star h psi, okay. Psi dot is by no, actually no I, no I psi dot, this is a I h bar psi dot is Schrodinger equation h psi, no, I am getting rid of h bar. So, I h bar psi dot is h psi. So, there is no I here, okay. So, psi star h psi plus, well, if you like you can put half a psi h psi star, but they will give the same, this is a real quantity, okay. Okay. So, this should be basically, yeah. So, this is my stuff, current, this is not energy yet, okay. This is a current J0. Now, of course, the integral of J0 is constant. There is another component of J which is, let me write. So, this is other component of J. So, we will get 4 components of J, right. J is, I mean, remember the J was this one, I do not want to go back. So, J has 4 components, I wrote del mu J mu is 0. So, this is the first component and these are the other 3 components, and other 3 components I need to compute pi k, the space momentum and psi dot, okay. But I do not need to worry too much about it because I am looking for conserved quantity. So, conserved quantity is this quantity, integral of this with space. So, if I integrate this, so I is gone, integrate this with space, what will I get? Is energy, no, is not it, this energy psi h psi, which is integral, this integral. So, this is energy, okay. So, we are able to derive conservation of energy by time translation of the wave function, okay. So, of course, there is one constraint that if I apply some magnetic field in Hamiltonian, then delta L will not be unchanged. So, there are some systems, for example, if you, okay, for not every time your time translation symmetry is applicable. Imagine that in the setup I put in a current which is changing with time, okay, external current, then electromagnetic experiment energy will vary with time, no, energy will not remain the same. But take a proton and electron and there is no other electromagnetic field outside, then energy is conserved during the experiment. But if you put, as soon as you put some external electric field, the energy will not be conserved, because energy will be, electric field will push in energy into the charged particles. So, here we have to make sure that this external fields are not present in H. If that is present in H, then psi will, this setup will not be invariant. So, delta L will change for those wave functions. Okay, so, that is a implicit assumption made here. Okay. So, I am saying that delta L is 0 for these variation of psi, that is a major assumption which is being made here, and that will not hold if the potential is introduced which will change the energy. Okay, so, in classical you can immediately understand, right, I mean I hope this part is clear. So, symmetry is not always valid. Now, let us look at space translation. I want to move fast. So, it basically follow the same logic, but I am going to shift not in time, but in space. So, you can think that I am shifting the setup, okay, I am shifting that by space. So, my delta psi will be d psi. Okay. So, here I apply the same logic, I need to rush bit, so 5 more minutes. So, no, actually we got to 6:30, no, 6:30. So, we have 15 minutes. Okay. So, now I am fine. I thought 6. Okay. So, let us look at the J0 again, that will give me conserved quantity. Okay. So, let us assume that for these variation of psi, under space transition delta L is unchanged, L is unchanged. So, delta L is 0. Okay. So, this is my Lagrangian. So, I can get these derivatives. So, pi 0. Now, my d psi is grad psi, right. I mean, this is straight obvious from here. It could be 3, it is a 3 dimensional field. So, there is a my variation can be in x, y, z. So, that is why we get gradient. So, pi 0 grad psi, and pi 0 we derived it earlier is partial L partial psi dot. So, that is that and grad psi, and I put complex conjugate. So, I by 2 psi star grad psi, okay, minus complex conjugate, right. So, this is straight away follows from there. Now, you may identify this object. This is looks like the Schrodinger equation current, no. For Schrodinger equation we can derive current, and that is exactly the current which you might have done in your quantum course, J Schrodinger equation. There is a okay. So, there is a factor half is coming here, there is a half is not there in the definition, there is half here. Okay. So, now if I integrate this, okay, so if I integrate this, what will I get? Integrate this object. So, what is the momentum operator? I h bar grad, no, there is a momentum operator. So, this momentum operator P. So, what is the average expectation value of P? Psi P psi, no. So, that is nothing but that. Well, I need to add, otherwise it will become complex. So, I need to add the take the real part of that. Okay. So, this give us total momentum. Okay. So, this variation space transition in psi which conserves delta, which does not change L Lagrangian density, will give me conservation in momentum. Okay. It is nice, no, it is beautiful. We just this symmetry immediately implies the conservation law. Okay. So, we done 2, conservation of energy and conservation of momentum, and linear moment, angular momentum follows from rotation. Okay. So, that can also be done, I will not do it right now, but we can do it by rotation, which is there in, I mean, you can find, you can do it yourself, that is a good exercise to do. Now, third one, which is slightly more complicated. So, we can change both space and time simultaneously, space time. Okay. So, this is in relativity, we change both space and time. So, that is why we have this 4 space time variation. So, this delta x nu is a space time translation. So, my wave function will go like that. Okay. Now, here I am using the notation for relativity. So, this is a dot product, but it is a 4 space time dot product. So, covariant, this covariant and this this contravariant and covariant derivatives. Huh? Okay. I have slightly messed up in my, okay, no, I think I am okay. Yeah. So, this is delta L. Okay. So, this is a Noether current. Now, we write delta psi from here, delta psi I just get it from there, and this is I just substitute here. Okay. Now, we can also, okay. So, now take the derivative of this, actually this bit of I have taken this guy out, delta x nu. Well, I think I am doing approximate derivation. Okay. I mean, there may be some algebraic error, but let us just take. So, this is from here it follows that partial L partial x nu, this is partial L partial x nu will be this object. I am slightly doubtful how can we take out this object outside. Okay, that is what is my doubt. I have taken this outside the derivative, but let us ignore that complication. Okay, so this is a partial L partial x nu. Okay, x nu could be, it can be time variation, space variation, all together. It turns out with this variation I can get both energy conservation and momentum conservation in one shot. In earlier derivation I was doing separately space translation and time translation. It turns out you can do it simultaneously. Okay. Now by definition we can write this, I am just changing the change of variable, well not change of variable, I am just introducing a delta function here. Okay. And if I, now these two must be equal, well sorry, subtract this a minus b. So this a and this b, a minus b, subtract it, then I will get that. Okay. So I don't right now, I am not equating this to 0, but I am just subtracting these two guys. Okay, and I get by definition 0, and this object is called space time tensor, space time energy momentum tensor, energy momentum tensor. Okay, and so that is a derivation of energy momentum tensor. Now this T mu nu. Okay, and the 0th component will be T00, which is nothing but Hamiltonian. Okay, pi phi dot minus L is Hamiltonian, and the 0k component is a linear momentum. Okay, so that's, so both this quantity if I integrate in with three space dimension, I will get conservation of energy and conservation of linear momentum. So this is a combined transformation. Okay, so it is more algebra, but it is same content what I did 2 slides earlier. Now the next one is non-trivial, it is called gauge symmetry. Okay, so please pay attention to this. I mean, this is you have not seen it before, I believe. So in psi, I can multiply e to the I theta, and this can be function of x y z. Okay. So let us assume that under local, by multiplying this, my physics remains unchanged. Okay, so let us assume that. So mod psi square will remain unchanged with this, but I am doing a very non-trivial operation. I am multiplying the wave function by e to the power I theta, and theta is varying in space time, space, not time, space. Okay. So with this, what is the change in phi? Change in psi? This is change in psi for small theta. Let us assume theta is small. So this is change in psi. Okay. So by the way, remember I was making a small change in wave function, not arbitrary change. So the d psi is I psi. Theta is of my parameter lambda. Theta is parameter lambda. So my current J mu will be pi mu del d phi, which is I psi dot, I psi not psi dot, I psi. Okay. So this is coming from here. So my Lagrangian is that. So I need to basically use Lagrangian to compute pi mu, momentum component. So momentum I know already that it is psi star and psi, right? I mean that's the stuff, and this is d psi, d psi is I psi. So psi star, I psi and complex conjugate, but I becomes -1. Okay, so I get minus half here and minus half here. So I get minus mod psi square, which is minus density, right? Wave function density is a probability density. What about the other component jk? 1 2 3 pi k I psi, but pi k is a momentum in the space dimension, which is nothing but grad psi star. Okay. by 2m. This is the momentum, no, I mean the momentum, so which is gradient operator for Schrodinger equation. So that and complex conjugate, but this is nothing but the minus sign, okay, by definition I checked the minus sign, minus of the Schrodinger equation, the current in the Schrodinger equation. You have seen this, no, this is a current, this is called current, yes. Now what does divergence of J give you? So take the divergence. So there is a minus sign, there is a only change of well, minus minus we can ignore that. So dt rho plus divergence of Schrodinger equation current is 0. So this you have seen it before, no. This follows, I mean this you can derive from straight from Schrodinger equation, but it follows from some symmetry principle, that if I change the wave function phase of a wave function arbitrarily small, then that does not change the physics, and that in fact this conservation law follows from that that symmetry operation, okay, current conservation. And well, of course the first component again should be give you a conserved quantity, and if I integrate this one I will get, well, this is trivial, no, the probability density integral over space is 1, okay. So that gives me constant, okay. So so this is called nonlinear Schrodinger equation, which is we use it for superconductors, super fluids. So it is same equation plus this quantity, okay. So this nonlinear is psi, but we write this as V psi psi. So V psi is mod psi square, no, correct. V psi is function of psi itself. V psi is normally we think of potential as function of x in a typical Schrodinger equation, no, Coulomb potential or delta function, or but here we make V psi psi itself. So this is a nonlinear, everybody agrees with that, it is a nonlinear equation. So this is V psi. Now whatever I showed you in the earlier slide, so we have several conservation laws for Schrodinger equation. One is mod psi square integral dx is constant, d cube x is conservation of probability density. This is obvious, I mean that's, but the other ones are energy conservation, which is psi h psi. We can also derive energy for this equation, okay. Now energy is slightly non-trivial, you can derive energy, which is this quantity mod psi square coming from here plus, well, g is 1 right now, for I put a g here. So g psi 4 Hamiltonian you have to derive for this quantity, and this is Hamiltonian for nonlinear Schrodinger equation, and this will be conserved under evolution. And linear momentum is, in fact this is somewhat straightforward, but this is also conserved.